This is an introductory lecture on the matrix displacement method for analyzing statically indeterminate structures. Our point of departure here is the slope deflection formulation, as it forms a basis for the matrix method. But initially, we're going to limit our discussion to the analysis of continuous beams only. We'll expand the formulation in future lectures for dealing with other types of structures. To begin, please review the slope deflection method presented in lectures SA 27 through SA 33. You also need to be familiar with basic matrix notation and operations, as we are going to write our equations using matrices. Consider this particular continuous beam. If we were to analyze it using the slope deflection method, first we would have written the slope deflection equations for each member. Then, we would have used the joint equilibrium equations to find the unknown rotations and displacements. In this lecture, we are going to, more or less, follow the same process, but we'll do it using matrices. First, we write an expanded version of the slope deflection equations for each structural member in matrix form. Then, we combined the member matrices to form the joint equilibrium equations, also in matrix form. The solution for this system of linear equations is the set of unknown slopes and deflections at the joints of the structure, which can then be used to compute member end forces. Please keep the parallels between the slope deflection method and the matrix method in mind as we go through the formulation. Consider a typical beam segment subjected to a uniformly distributed load. Here are its slope deflection equations. They give us member end moments in terms of member end rotations, theta, and the relative end displacement, delta. Let's number the equations 1 and 2. We also want to represent the member end shear forces in terms of theta and delta. For this free body diagram, we can write sum of the forces in y direction must be 0. Sum of the moments about end I must be 0. Solving these equations for Vij and Vji, we number these equations 3 and 4. Here are our 4 equations. Using 1 and 2, we can rewrite 3 and 4 as these equations define shear and moment at the two ends of the member in terms of end slopes, theta I and theta j, and relative displacement, delta. Let's replace delta with the end displacements for the member. If we denote vertical displacement at end I as delta I, and refer to the displacement at end j as delta j, then we can write delta equals delta j minus delta I. Substituting delta j minus delta I for delta in equations 1 through 4, we get. Now, I am going to reorder these equations before rewriting them in matrix form. The first 2 equations give us shear and moment at joint I, and the second pair of equations is for shear and moment at joint j. In matrix notation, these equations can be written as this is called member stiffness matrix. This is member end force vector. This is member end displacement vector. And this is fixed end load vector. Now, let's apply this system of equations to each beam segment. For member AB, we get since the segment is not subjected to any loads, the fixed end load vector consists of 0 elements only. We can further simplify the equations by setting delta A to theta A to delta B to 0. That is, since A is fixed, displacement and rotation at that end of the beam would be 0. And since there is a roller at B, we know there would be no vertical displacement at that joint. So the system of equations can be written as. Here, we have substituted 0 for delta A, theta A, and delta B in the member end displacement vector. It is important to note that, in this lecture, we are ignoring axial deformation. That is why axial forces are not present in our equations. We will bring them into this formulation in future lectures. We can shorten the member end force vector by removing the 3 zeros and by adjusting the stiffness matrix accordingly. Here are the equations for member AB, and here they are in compact form. Since the first column of the stiffness matrix represents the coefficients of delta A, the second column represents the coefficients of theta A, and the third column represents those for delta B, we can remove them from the matrix and rewrite the equations in compact form. And in case you were wondering, here are the exact same equations in algebraic form. For member BC, we can write since delta B, vertical displacement at B, equals 0, we can rewrite the equations as. Here, we have replaced delta B with 0. Rewriting the equations in compact form, we get we achieve this by removing the 0 from the force vector and by removing the coefficients of delta B from the stiffness matrix. Let's summarize what we have done so far. Given this beam, we have written an extended version of the slope deflection equations in matrix form. Here are the equations for member AB, and here they are for member BC. These equations give us member end shear forces as well as bending moments in terms of slopes and displacements at the end joints. Now, let's turn our attention to joint equilibrium equations. For this beam, we have a total of 3 unknowns: theta B, delta C, and theta C. We say that the beam has 3 degrees of freedom. How many equations do we need for finding the unknowns? We need 3 of them, 1 equation per degree of freedom. Since in this formulation we are only considering bending moment and shear force, but not axial force, we can write 2 equilibrium equations per joint. Sum of the forces in y direction must be 0. Sum of the moments at the joint must be 0. The beam has 3 joints. Therefore, we can write up to 6 equilibrium equations, but we only need 3 of them. Which ones do we need to use? Simple. We use the equations associated with the degrees of freedom of the beam. Here, rotation at joint B is one of the degrees of freedom. So, we use the moment equilibrium equation at B. Since bending moment and joint rotation go hand in hand, they are cause and effect. Another degree of freedom is the vertical displacement at C. For this, we need to look into forces in y direction. So we write, sum of the forces in y direction at C must be 0. And we use the moment equilibrium equation at C since theta C is a degree of freedom. Here are the 3 equilibrium equations in terms of member end forces. Let's expand them using member matrices. In the first equation, we have MBA and MBC. We find MBA in the equations for member AB. Here are the equations in matrix form, and here is MBA in matrix form. For MBC, we need the equations for member BC. Here they are. And here is MBC in matrix form. So, the two terms in the first equilibrium equation are... How do we add them together to get the first equilibrium equation? Like this. This is the sum of the coefficients for theta b in MBA and MBC. This is the sum of the coefficients for delta C, and this is the sum of the coefficients for theta C. To better understand this addition operation, let's view the equations in algebraic form. Here is the first equation. Here is the second equation. And here is their sum. It equals 0. You may want to spend a few minutes here examining the relationship between the two notations. Here is our second equilibrium equation. We need VCB in matrix form. Here are the equations for member BC. VCB, the third equation in the set, can be easily extracted from the matrix, so we can write to write the third equilibrium equation, we need MCB. Here it is. Therefore, this becomes our third equilibrium equation. Given the three equilibrium equations in matrix form, we can concatenate them to get our system of linear equations. Let's write them this way. We can find the unknown joint rotations and displacements by solving these equations. This is called system stiffness matrix. This is system displacement vector. And this is system force vector. There are various methods for solving such system of equations. If you are going to solve this by hand, Gaussian elimination method would be a good technique to use. I am going to assume that you know how to solve this already and just present the results here. The solution for this system is... Now that we have determined the unknown slopes and deflection, we can substitute them back in the member-specific equations in order to find the member end forces. For AB, here are the equations for member forces. Here is the solution vector. Substituting this value for theta b, we get these member forces. Let's use them to draw the member's free body diagram. For BC, we can write, substituting the solution vector here, we get here are the member end forces for segment BC, and here is the segment's free body diagram. Now, let's determine the support reactions for the beam using the segment free body diagrams. Here they are. Finally, we draw the shear and moment diagrams for the entire beam. See if you can analyze the following beams using the matrix method.